So today let's look at simple AC circuit. And first of all, what is simple AC circuit? So we can define simple AC circuit as, an AC circuit is the loop of a metallic conductor through which an alternating current flows. And of course we have two types of currents. We have DCs and ACs. So we define AC circuits as those circuits, AC circuits are those circuits through which alternating current flows. And of course, alternating current can be shortened into AC, and that's the meaning of it. So what does it look like? A simple AC circuit is given below. The diagram of it, we have something like so where we have this. So this diagram here gives a simple diagram of an AC circuit. You see, so the difference between an AC circuit, a simple AC circuit, and a DC circuit is this figure here, this symbol here. This is a symbol for an AC source, where all where all components have their usual meaning. That is, this is for voltmeter. This is a resistor. We have this, meaning an ammeter. And then we have this one to mean an AC source. You see, so this one here is a voltmeter, a resistor, an ammeter, and an AC source. Now, if this diagram were to be that of a simple DC circuit, we're going to have something like this, which people are more familiar with. And of course, this symbol here is a battery or a cell. It's a source for a DC. So we say an AC circuit is that loop of metallic conductor through which an alternating current flows. Through which an alternating current flows. Okay. So what is an alternating current? So we define an alternating current AC for short as the current whose value at any point in time varies. So an alternating current AC is that current whose value at any point in time varies. You see, and its direction can be reversed or is reversed. Unlike the DC direct current, which flows only in one direction, an alternating current flows in both directions, so that there is no net movement, no net displacement of the electron in any given direction. You see, this is as opposed to a DC, which is direct current, which flows only in one direction. See, but for an alternating current, there is no net displacement of the electron in any given direction. It oscillates about a fixed point. You see. Okay. So an AC circuit, so an alternating current is mostly represented by a sine waveform. Yes, an alternating current is mostly represented using a sine waveform, and that means it flows sinusoidally. And what we mean by that is this: if we plot a graph of an AC, an alternating current, on the vertical axis and time at any point in time, remember we say an alternating current is that whose value changes as time progresses. So if we plot a graph of alternating current with respect to time, you get what we call a sine waveform. That is, it is sinusoidal. You see, where here corresponds to the peak current, which is I0. Now, there are other ways through which or by which an alternating current can be represented as well. It's just that the sinusoidal waveform, the sine waveform, is the most commonly used representation of alternating current. Other ones could also include a triangular, which appears something like this. Or we can also have a rectangular waveform which goes something like this. You see, so an alternating current can be represented on a graph using any of these three forms, but the most commonly used form is the sinusoidal, or is the form of a sine wave. This is more common than all the other ones. Okay, so just to recap what we've done here, we say an alternating current circuit, that's an AC circuit, is that loop of metallic conductor through which an alternating current flows. You see, so the kind of current that flows in a circuit defines what kind of circuit that is. If it's a direct current flowing through it, then it's a DC circuit. But if it is an alternating current flowing through it, then it's an AC circuit. And this is a simple diagram of an AC circuit, while this one here is a diagram of this DC circuit. And of course you can see the difference is the source of power in that circuit. In this circuit here, we have this symbol here, which tells us this is an AC source. It's an alternating current flowing through it. And here we have a battery or a cell, more appropriately a cell, flowing through this, which gives us this tells us this we only have a direct current flowing through this place. So now we have to go on to the next thing. Okay, remember I said an AC circuit is mostly represented using a sine wave form. Now mathematically, instantaneous current in an AC is always given as I naught sine 2 pi f t. Let's call this one equation 1. So this is the formula giving the instantaneous current at every point in time. You see, so when you plot the value of the current against every point in time, you're going to get, using this formula, you're going to get the sine wave. If you plot it on a graph, you're going to get the sine wave, you see, which is what we treated a while ago. Now, in this case, this I here, where I is equal to instantaneous current, I naught is peak current.
Which one is here?
Of course, F is frequency of the AC source.
Yeah, that's by 0.
And then T is time. So I is instantaneous current. That is the value of the current at every point in time. I naught is peak current. F is frequency of the AC source. And T is time. So now, but remember that omega is equal to 2 pi f. So we call this one equation 2. Now if you put equation 2 into equation 1, putting 2 in 1, we have, so our instantaneous current
when there is a difference in bank G
is equal to peak current sine omega t. You see, so the whole of this 2 pi f comes off and then replace it by omega, where omega is, in this case, omega is not okay, omega is angular frequency. Not angular velocity, please. You know, we are used to seeing omega to be angular velocity. That is when we're talking about describing the motion of a particle in a circle.
Is there any difference?
When we are describing the motion of a particle in a circle, then this omega here could mean angular velocity. But when we're using it to describe an AC current, there's an alternating current, the omega is no longer velocity but angular frequency. You see?
Closing balance for match.
Okay, so let's say example 1. An alternating current.
Yeah, I agree with you, but unless I see it, I may not be able to.
Is given
Do a departure.
by the equation
But
I is equal to 4 sine 10 pi 10 pi t. Find the following. 1. The peak current. 2. The angular frequency. Then 3. The frequency of the AC source.
Is
You
it
see? So
is it balanced?
so an alternating current is given by I is equal to 4 sine 10 pi t. So find the peak current, the angular velocity, so the angular frequency, the frequency of the AC source. So this is a rather very simple question to solve. So what we're going to do is this. You know, an AC circuit, the instantaneous value of an alternating current is given as I naught sine 2 pi ft, or I equals I naught sine omega t. Now from the question, the alternating current was given as I is equal to 4 sine 10 pi t. Pi t. So what we're going to do now is just to take correspondence. We have to take correspondence here. Now if you look, to answer our first question, find the peak current, which is I naught. When you compare this equation to this equation, you see that I naught corresponds with 4. So our I naught is very easy to read it off. It gives us 4 ampere. Again, I naught means peak current.
Not yet.
Now number 2. The angular frequency, which is omega. Remember I told you that omega is angular frequency. Okay. So omega here is, from here we can easily see that omega is the same thing as 2 pi f, and from here it corresponds to 10 pi. So we have 10 pi is our omega, 10 pi radians per second, or we can say omega is equal to 220 all over 7 radians per second. Any one of them is fine. The omega here corresponds to 10 pi, and that means omega is equal to 10 pi radians per second, or omega is equal to 220 over 7 radians per second. Of course, if you want to get a decimal here, of course you know how to divide it. You divide this by 7, you get your answer. And then number 3, the frequency of the AC source. Now remember that omega is equal to 2 pi ft. No, sorry, 2 pi f. Omega is 2 pi f. Now from here we have, okay, 10 pi is equal to 2 pi f. This pi will cancel this pi out, and then we have these two will take this 10 out, and so we now have f is equal to 5 hertz. That's our answer. That is, remember that omega is equal to 2 pi f. So to find our angular frequency, to find our frequency, the frequency of the source of the alternating current, we have to equate this to this. And of course from here we know that angular frequency is 10 pi, which is here, is equal to 2 pi f. So if you cancel this pi and this 1 out, take this 2 away from this, so divide 10 by 2, we get f is equal to 5 hertz. It's as simple as that.